Okay, a problem that we really like to use in IB physics in the option A topic, if you are in SL, is something like this. Let me move this down. Say we have a surface of water here, okay? And we hold a tuning fork above the surface of the water, and we strike it so that it vibrates like this. Yes, vibrating, good. And of course this produces a wave, right? So let me just draw the wave like this. Here's the wavelength of that wave, right? And this is the equilibrium position. Okay, now this represents the wave created by the tuning fork. Of course, the tuning fork produces a sound wave, so that produces compressions and rarefactions. And a sound wave, in other words, is a longitudinal wave. So it does something like this. Oh, there's a big, big compression, lots of particles all next to each other. And then they spread out a little bit. And then they get really dense again. Compressions and rarefactions, right, like this. But we represent the left-right displacement of individual particles using this. Right? So maybe this means so an individual particle here is going to vibrate up and down, and so the left motion here represents that it's gone down, let's say, and the right displacement represents it's gone up, something like that. Right? Okay, at any rate, we have this wave, and I'm representing the wavelength like so. Okay, if you were to take a tube and place a tube in the surface of the water, and then just bring it out, maybe let's say to here, right? Then the wave would come traveling down from the tuning fork. It would strike this barrier and be reflected. It would go down, right? It would hit the barrier, and then it would be reflected back up. And the incident and reflected waves will interfere with each other, or superpose, or add together. And if the length of this tube meets certain boundary conditions, then a standing wave will be produced when these two interfere, the incident and the reflected waves. So let me explain this like so. We know that for a wave, a standing wave to be produced, in a pipe which is open at just one end, because this water barrier forms a closed end of the pipe, it might as well be a wall that the sound can't pass through. Of course, some sound does pass through, but imagine we're only focusing on what's reflected back. So for a pipe which is open at one end, let me draw it, right? Here's the closed end, here's the open end. For this pipe to have a standing wave formed, there's an antinode here and a node here, which means it has to look like that, right, for the wavelength. So if I were to keep going, I could draw the wavelength up. So let me pull this down. There we go. Okay, a common problem we like to ask in IB physics when we're learning about standing waves in option A. Let's say we have a surface of water like this, and we have a tuning fork placed above the surface of water, like so, and we strike the tuning fork, right? And it produces these compressions and rarefactions. The tuning fork vibrates up and down, and so the air particles here get scrunched together or compressed. And then when the tuning fork, so that's what happens when the fork prong goes down. When the fork prong moves back up, there's an open space called a rarefaction. So we end up getting this pattern like this, right? There's a compression like this. The air particles are close together. Then they spread out, and then they get really spread out. And then I'm going to run out of room, so let me move my tuning fork back up a little bit higher. Then they come back together again. They compress, right, like this. And we get this pattern of compressions and rarefactions, right? And they should all be, I don't know why I'm doing this, this is interesting. For some reason, these should all be a straight column up down. They're not supposed to be spreading out and like they are. Right, so they spread out like that. Now, here's a compression, here's a rarefaction, here's a compression, here's a rarefaction. So we could describe this longitudinal wave, consisting of compressions and rarefactions, using a sine curve, right? Here's my curve. We are at a maximum density right here, and then we come back to equilibrium, and we reach a minimum density right there, and we come back to equilibrium and a maximum here, right? See how it's really, really compressed there? Now, I'm going to erase this and just show one complete wave, like that. And the dotted line represents the equilibrium position. So what I've done is I've said, look, this is where density is at a maximum. This is an equilibrium position. Here's where density is at a minimum. This is another equilibrium position. This would be another maximum. Okay? So I'm using my sine curve to represent the compressions and rarefactions. So we can use a sine curve to represent longitudinal waves. Good. Let me take away these dots. And I'm going to move my tuning fork back down. If you were to take a pipe, right, which is open at both ends, and if you were to place it in the water, I've got a green pipe here. Well, if you let me make my pipe a little bigger. Make it like that big, let's say. If you strike the tuning fork above the pipe, then the wave will go down into the tuning fork. It'll hit this barrier, which might as well be a wall, and it'll be reflected back. And this reflected wave will then meet a subsequent incident waves. So the tuning fork keeps vibrating, it keeps sending waves all the way down, 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 down. And those down incident waves interfere with the reflected waves. And if they interfere, then they might be able to produce a standing wave, right? They might be able to make a standing wave. That doesn't say anything. Okay, imagine that says standing wave. How do we know when a standing wave is produced? Well, certain boundary conditions must be met. Right? So let's say here's my pipe open at one end, like that. The boundary conditions for a pipe open at one end are this. There's a node at the closed end of the pipe. And this is a displacement node, because particles, air particles at the closed end, they can't move up or down. They're fixed in their position. The other boundary condition is that there must be an antinode at the open end, because that's where the air pressure can allow these particles to just move back and forth as far as they can go. Right? So there's no buildup of air pressure, so they can move as far as this column will push, as far as the pressure that builds up in here will push. Alright then, let me move this down. Here's what it looks like to have a node at this end and an antinode here. Looks like this. Okay, that's a pretty ugly wave, but imagine it's nice and smooth. There's the antinode, there's the node, here's the next node, here's the next antinode, and the next node, like that. Right? So let me erase. If I come back over here then, right, back to my wave, well, I could draw how high the pipe must be in order to produce a standing wave for this guy here, for this wave. Right? Here's the first antinode. So the pipe has to extend that far. Like that. And now there will be a node here at the water surface, and this is an antinode here. So when this length of the pipe equals the wavelength over 4, right? Because this is 1/4, here's the next quarter, here's the third quarter, here's the fourth quarter. So from here to here is a quarter wavelength, because this whole thing, one full cycle, makes a wavelength. When L is lambda over 4, that's when we get our first standing wave. Now, air particles vibrating back and forth like this produce sound. And when we have a standing wave, the sound gets really loud. Okay? Kind of like resonance. It is resonance within the pipe. So this thing, when we have the boundary conditions being met, the pipe will reflect, the wave will come down, it'll reflect back and forth, and it'll produce this standing wave with a really loud sound, right? Because it keeps reflecting back and forth, because these boundary conditions are met. And so this standing wave propagates, and it continues, and it keeps going. So we hear a loud sound. If you pull this pipe out, when is the next point where we will have a standing wave? Well, if we pull it out to here, we won't get a standing wave, because we would have 2 nodes, and we need an antinode here at the open end. So we have to go farther than that. We have to go all the way out to the next antinode, right? So if you pull it out to here now, yes. And imagine my tuning fork. Let's see, there we go. Oh, so many tuning forks. Delete. So I strike the tuning fork, right? Waves are sent down into my pipe, sent down, they reflect back, and then the incident waves interfere with the reflected waves. They interfere to produce a standing wave. And it looks like this. I'm drawing from here up like there. Alright, so I have an antinode here, and I'm going to have this, a node is at the water. It looks like that. That's pretty good. That's decent. Looks like what I've got over here. And in this case, now, the length, which is different from this length, these are different, is how many wavelengths? Well, here's a quarter of one wavelength. Here's the next quarter, and here's the third quarter. So it's 3/4 of a wavelength when the pipe is this distance from the water, right? Raised this distance. Good. Almost done. So what we notice is, let me take this, and oops, can't move that. What we notice is that if you were to take the pipe, right, and move it to any distance, there will always be a node at the water surface. Node, because air particles which hit the water surface will not be able to move when they're right there at the water surface, right? The water surface prevents them from bouncing around back or forth. So they stay at the exact same position. Because they can't bounce back or forth, the water surface prevents that. Now, if you were to pull this pipe halfway between these two positions, like, oops, let's say you were to pull it out to here, you would not have a standing wave form. Here there's a standing wave, check. Here there's a standing wave, check. And in both of those cases, the standing wave will continue reflecting back and forth and producing this loud, resonant sound. But right here, there won't be any reflection back and forth and interference producing a standing wave, because the boundary conditions aren't met. So the wave would just come down like this, come down, and then reflect right off, and you wouldn't get this back and forth reflection like you do get over here and here. So you won't hear a loud noise when the pipe is at this height. Okay. So we understand, whoops, dropped my mic. We understand now that the node, there will always be a node at the water surface, and we understand why a standing wave is formed, and we understand why there won't be a standing wave when the pipe is at this height, because the boundary condition won't be met. Let's say we're told that the frequency of the sound coming from the tuning fork is 932 hertz. That's a B flat. And a B flat is my favorite note. No, B flat is the favorite key for jazz piano players to play in. They like that key, B flat. But my favorite note is a D flat, because my name starts with D. Alright. That's not the real reason. D flat. Nice, dark, mellow sound, D flat. Okay. Here's my frequency of the sound that's leaving the tuning fork. I'm also told that I start pulling this tube out, and when it gets to here, I stop, right? I hear a loud noise and I stop. Then I keep pulling it out, the sound diminishes, and then it gets really loud again. Okay, so I'm here now. The distance that I lifted the pipe between the two moments when it was loud, that distance which I raised it, or elevated it, is 17.7 meters. Using this information, I have to estimate, or calculate, the speed of sound. Well, take a look. This L prime minus L equals 17.7, right? This minus this equals the remainder, 17.7. So I could say that 3 lambda over 4 minus lambda over 4, since this is lambda over 4, this height, and this is 3 lambda over 4, equals, oops, wait, this is wrong, this should be centimeters. I've been given my value in centimeters, so I'm going to have to convert. Okay, so I'll go ahead and convert from here to here. In meters, it's 0.177. Okay, so if you subtract, what you get on the left is lambda over 2 equals 0.177 meters. Yikes. And let me move some things around since I'm running out of room here. This must be the greatest feature of Smartboard. You can just move your text like that to make more space. So lambda, if you multiply left and right by 2, you get 0.354 meters. Good. So how do I find the wave speed equation? Oh, I gave it away. How do I find the wave speed? You use the wave speed equation, F times lambda. So you plug in 932 hertz, right? You plug in lambda, 0.354, and what does the answer come to? Let's get out our trusty calculator. 932 times 0.354, and that's, wow, 330. That's a pretty accurate value for the speed of sound. Clearly this problem was engineered to produce a nice, pretty value, which is very close to the true speed of sound. Okay, so that's how you solve. You're given this distance. We know that that distance is half of a wavelength, because it's this minus this. Really, you don't need to show these steps if you were solving this for credit on an IB test. I believe all you would need to show is what's in blue down here. Although it's it's always good to show these steps. Show this step as well. You don't need to show this, obviously, but 3 lambda over 4 minus lambda over 4. That's a good thing to show in general. Check. Good work.